Um, so welcome back. And as we talk about this kind of end of semester timeline and goals, I neglected to really officially bring up the projects that I want every team to do this semester. You would have seen it in Canvas, and maybe many of you read it, but I haven't received any questions yet, which led me to believe that maybe you've looked at it, but not really looked at it too closely as of yet. So this document is up on Canvas. Um, and in terms of an assignment, there's this sort of zero credit but necessary assignment where you put in a project proposal. This is technically Tuesday of week 9. It will not be due Monday of week 10. You do need some time as a team to think about this, not just quickly put something together. So we'll make that due Monday of week 11. I just don't feel like updating the PDF, but the Canvas deadlines will be updated accordingly. And the idea of this is that we have these MP assignments where I think as we go along, and I've been providing you less and less, in terms of structure, in terms of starting code. And with MP4, it looks like we're going to provide one file for MP4 because the compiler isn't quite 100% ready. But other than that, basically for MP4, if you look at that document, which I know we're getting a little bit ahead of ourselves, if you look at that document, it says, here's what you need to do, figure it out. Which is probably a more realistic thing to be working on than following and trying to reverse engineer what I mean when I say something to try to understand my code from a lot of students assume that when it's a piece of code I provided that means it's really good or really clever. Sometimes that's the case. A lot of times that's not been the case. So you're going to be doing a lot less mind reading, for MP4, and then this leads into the project, which you can think of as an MP5, and it's an MP5 of your choosing. That'd be one way to think about that. So in terms of the scope of what I expect teams to do, given the time that we have remaining this semester, you can think of that as the 2-week plus lab assignment. What I think will be fun about it is teams then get the opportunity to decide what that's going to be. What you would like to work on that's not currently in the SGP infrastructure, how you'd like to split up the work, and you get to define success as well. So let me walk through this document just pretty briefly here because it's relatively self-explanatory, but I want to get to the parts at the end. I think it's worth spending a couple minutes today on that before we dive into our Learning Module 6 topic here. So you will be expanding on some portion of the simple graphics processor design. At least in theory, what you would be starting with would be an MP4 base, and everyone would be roughly starting on the same base. We'll see. Based on how MP3 is going, we'll see how MP4 goes as well. But certainly, I think you can assume an MP3 base of vertex shading working, and then you're going to be adding to that. Um, I definitely want to mention that there's a lot of teams who really want to do innovative software things, and I think that's wonderful as well. There should be some hardware aspect of this as well. This is an architecture class, so have some hardware and some software aspects. Um, the assumption is that you're going to be working with your existing teams. The teams seem to be working pretty well all semester. Um, when I teach a class like 381, a big chunk of my job is dealing with teams that aren't functional and trying to combine teams and replace teams and just you know lots of unhappy teammates. And in this class, it's just not happening. So that's wonderful. I think probably at this point we're just going to have two presentations given the time we have remaining. I reserve the right to have us do an extra presentation, but we're talking again these 5-minute presentations. You shouldn't be putting lots of time into them. So this project proposal presentation, it's not a demo day for us, but that's what you'll be sharing with the rest of the class. What you've been proposing for your project, you get to see what all the other teams are doing as well. And then certainly that is what we're going to be doing for our scheduled final exam time for this class, right? There's no exam. We're expected to meet as a class during that time if there is no exam, and that's what we'll use this time for. It's additional time available to us. I think it's 2 full hours. And we'll probably wind up using that entire time block to do our final demo day. Presumably, because everyone's doing something different, it's less of, well, our implementation is exactly as the previous 3 teams. There will be less of that, so the presentations will take a little bit longer. And I think you'll be really proud of what you're working on, so you'll want to spend more time on it. So we've had these rubrics for MP1 through where we are right now. And a lot of you have mentioned a lot of the points are based on the write-up, and that was intentional. I want you to put good faith effort in implementation, to describe what you're doing architecturally, to explain your testing strategy, and to provide some level of results in the report. For these assignments, you get to decide as teams what success is in terms of the actual grade that you are receiving. Um, some of you may be wondering, well, that could be easily gamed and we can all give ourselves A's. That's okay. In my experience, it's the exact opposite that happens with this kind of thing. And I'll probably, if I provide any critical feedback of your project proposals, it'll much more likely be for that reason, which is you're proposing something that's too hard. You're going to get a very bad score, even if you put a ton of work in with the rubric you provided. So be reasonable, be fair. I don't think I've ever, and I've done this in many different classes over the years, with team proposed rubrics for projects. I don't recall ever telling a team that their project was too easy. It's almost always the other extreme, too harsh of a rubric or too difficult of a project, in my opinion. And we try to scale things back accordingly after the initial proposal time. So there'll be no single fixed grading rubric, but the team is going to have to put some thought work into what should go into the rubric. You do actually need to spend some time on it. Don't just spend 10 minutes on that. Spend a couple hours as a team discussing, maybe doing a little exploring of what is feasible, what's not feasible, doing a little research in advance so that when you put together a rubric, it is sensible. It's something you can actually accomplish, and it's going to add up to 200 points. So it's roughly scoring wise 2x an individual MP, and then we'll be doing some sort of peer assessment during that final demo day. So your grade will be 50% based on your peers' assessment and 50% based on my assessment. So beyond that, a rubric that adds up to 200, something that is hardware and software and related to the class infrastructure, related to the class, what we've been doing this semester. Beyond that, you have a lot of flexibility, which I know can stress some of you out, right? It's a little easier when I tell you do exactly this, but I'm not going to tell you that. I can give you more ideas. Um, the truth is there's hundreds of ideas that make sense. There's a lot of missing things in our processor and in the infrastructure surrounding these labs. And I don't want every project to do that, but I think if maybe 3 of the 8 projects are working on improving the infrastructure for next spring's offering of the course, that'd be wonderful. Um, Things like system-wide simulation is something we don't do at all right now. Adding more advanced OpenGL features, there's a large book of such features that you can consider. Um, some of which require little hardware and big software or big driver. Others are little driver and big hardware. So as a team, decide what you really want to work on and where you want to spend your time on this project. Um, something with using the microblaze processor for either debug or simulation or boot up screens or all sorts of things to make this a cooler demo target. There's a lot of ideas. This is not exhaustive at all. I put a couple ideas together and then thought, well, you guys will come up with cooler things. Maybe you've already been thinking about it. What you'll be submitting on Canvas, relatively brief, but I do want the team to think about it. So some of you may be thinking of it, well, the project doesn't start yet. I would like you to think of the project as starting today because the write-up should be very thoughtful. You really be introspective in terms of what's feasible for your team. I don't necessarily care about brilliant academic writing and that your grammar is completely on point and all that for this write-up, but I do care that you've thought about the scope of the project and what that means in practice. So this is the requirement for it. So the tricky part is this is worth 0 points. This actual write-up itself, but it directly influences what you'll be getting points for when you do your final submission of the final project. Really think about what the list of project goals will be. What does a successful project look like for your team? And I want you really to think about the timeline as well. And I do want you to take that seriously. I review so many senior design projects where the team doesn't take the project plan seriously, and on May 1st we'll get the entire project done. Is much of the project timelines that I see for senior design. But for this class, because you've been putting in these hours and you're a little tired and you know what it takes to get things working in practice, be honest, be thoughtful about what is reasonable for this and tie that into your rubric. Now, this rubric given here is intentionally one that doesn't make any sense. You can't use this rubric for your purposes because this is all about how we would implement fixed function lighting, and there's no need to implement fixed function lighting. We will have lighting at least per vertex lighting done after MP3 here, and hopefully per fragment lighting done after MP4. But this is the kind of thing that I would want your rubric to look like. So maybe you've seen this in other courses, but maybe you haven't. Um, a 2D table in which the rows are the various, and maybe we should use a different word than attributes. It's overloaded this semester, but components of your score. I put demo and report here. If you don't care about having a high quality report, you don't have to give yourself any points for the report, and maybe a presentation at least, because I think people will want to see the demo for it. Um, but really, what I'm talking about mostly is what is the functional aspects of your implementation of your proposed project. What are the main milestones you would like to see? They probably have some interrelation between each other, but there probably shouldn't be a strict dependency between them. That you can't start on attribute two until you've completely finished attribute one, because that'll set yourself up for some, at least some stress, if not potential failure there. So that's the rows here in this table are the components of your project. What are the real deliverables, the aspects of the deliverables from your project? And I think it's fine to think backwards from what would be really cool to demo for our final project demo day, but don't double count that as well, right? So if you have demo to demo things, then that really should be here in terms of what are the capabilities of it. That ties into what you're able to demo for it as well. And different columns here then representing how well you did on it. And I definitely suggest not having binary thinking for this. Like we have not all semester, right? Nobody's gotten a 0 on any individual component this semester. It's not pass fail. It's certain levels of progress made, certain amounts of functionality made. And I think you should then have at least 3 columns. If you have too many columns, it maybe becomes really hard to define what it means to be level 1, 2, 3, 4, 5. But 3, I think, makes sense. You've made some progress. If you've made 0 progress, then 0 is fine. But you've made some progress, but something's not working, or it's only working in simulation, or in terms of functionality, you only have a portion of the functionality you were hoping for. And then you would have this sort of satisfactory or accomplished middle column in your rubric here. And that's your goal. That would be your goal for the assignment, which is this is what I want to get done. What does a successful outcome for that component mean? So in terms of setting this rubric up, and if you do this wrong, it's fine. I'll ask you to revise it. It won't be that hard to revise it necessarily. But that middle column should add up to 200 points. You have satisfactorily accomplished this project. You've done everything you wanted to do. If you were to evaluate yourself on that, that should be then adding up to 200 points for your project. But then, just like we have a couple of these opportunities for the individual MP assignments, I'd also like your team to consider giving yourselves opportunities to also, if there's 3 different main components of the project and they're somewhat interdependent as they should be, you may have the opportunity to really excel in one aspect of it, whereas this other aspect you didn't quite get everything working that you wanted to. That doesn't require you give yourselves quote unquote bonus points for every category here. Um, but you should give yourselves opportunities to succeed so that 200 points doesn't necessarily mean straight down the middle column here. Maybe you did really well in the first attribute, struggled a little bit in the second, and then were satisfactory in the others, and you get yourself a score that is reasonable for this assignment. So that's an important part, and I do think it's not something I think you can just quickly spitball and say, here's what we're going to do for the project. I do think it will require some discussion, possibly some reading, possibly even some coding just to see what does this look like in practice from an OpenGL perspective. What would that then mean from the driver's perspective? You don't do it all now, but and then finally, what would that mean from the hardware perspective? So you get an idea of what the scope of this would actually require. So some discussion, some negotiation amongst the different team members for who will take on what role, and then collaborating on what this rubric is going to be. Because what will happen is we'll have this deadline, and you'll submit this, and we'll have our little presentation as sort of a mini project presentation day in 2 weeks, and I'm going to hold you to it. So that'll be your rubric for the project. So give yourself a rubric that you can succeed on. I am perfectly fine with every team getting 200 out of 200 on this project if it was a legitimate project. Some may be harder to do than others. Some may be really more nitty gritty hardware details than others. Some may have larger scope than others, and that's also perfectly fine. But again, as I mentioned in the beginning, in my experience, um, The risk is teams wanting to really impress me, perhaps, or just really just want to shoot for the moon, um, which I get. But keep in mind the scope of this, the time associated with this. This is not a 2 semester capstone project. If you have a really big idea, um, let's do a master's creative component on it. And then let's do it in that context. Let's take a full plus semester to work on it and write that up properly and do all that would be required to do for that. That This is not the time for that kind of really big ideas here. Um, and I do expect, and I hope to see some Q&A, maybe some office hours discussion before this is due. I'm happy to review anything before you submit it. I'll also review it after you submit it, but I'm happy to review before we have our presentation. So that took a lot longer than I expected it to. Any questions about this? You can speak up or you can type in the chat. Okay. Oh, Matt, no, I'm not going to do a 30-second recap of everything I just said. Fortunately, you can review the video once it's posted. And then you can also review this document, which is also posted, and let me know if you have any questions at that point. Um, 30-second version of this. We have a project. It's up to you. Do your best. You have to think about it, but don't be too terribly aggressive about it. There you go. That's even the 15-second overview of what this is about. Um, And I think in terms of the report, I do say a 1 to 2 page report because you do need to think about it. This is the most important part of the report. I'll have you put this in your slide as well. Here is the rubric that the team has decided upon, and here's what success is going to look like for us. It's that middle column in our rubric. Not today, Matt. Okay, so then I am going to move on. Um, and just jump into the lecture 6 kind of topic here. So I do understand that you're working on MP3, and I'm also asking you to work on this. I think there's probably sufficient, whether you want to call it downtime, synthesis time, time where while you're discussing things, you can also start ideating about what you'd like to do for this project. Um, don't wait till the last minute. It's worth 0 points, so I understand the temptation to kind of say, well, we'll do whatever we need to do at the very last minute. We'll do it Tuesday morning and put the slides together that day. But I would really like you, um, I'd really like you to put some thought into it. So, Micah, that is a totally valid question in my opinion. It depends what you mean by fixing. No, so if it's your own bugs, no, right? But if you found, and I think there's one team who could probably do very well with this, and your team as well. Um, which would be um lost my train of thought. Oh, which would be looking at what all the compromises we've made so far this semester as a class, not your own individual compromises, and saying, well, here's 3 things we'd really like to improve. um, that's perfectly reasonable. Optimization is also a possibility, but I think you have to be really careful and truly define what that means in practice. So I mentioned that as a possibility. Overall system kind of throughput or FPS optimization here. Could also be resource optimization, but FPS optimization. Trying to figure out what parallelism means here. That's a very hard project. It's doable, but then to do that, you would want to spend the time to really understand. Some teams have done a little bit of that, but where are the actual bottlenecks now? You can't optimize something if you don't understand it at that level, where you know where the flaws are currently and where to allocate your resources. Um, I would also think mentioned, and Ryan mentions OpenGL two. Well, we will never be fully compliant, but we already are compliant with OpenGL 2. If you're thinking about fixed function OpenGL, I think that's entirely in driver space. I think we could figure something out with that in the driver space. I'm pretty sure we're already capturing those calls, like GL vertex calls and the like, GL color calls. And I'm pretty sure in the driver, we could capture all those calls and then convert them once we get a GL end. There's ways to do it. Convert that call to the equivalent OpenGL calls that we support now. So that is doable. So as I mentioned, thinking about what you want for your demo, I don't want you to double count what your demo is, but thinking backwards from what you would like to demo. is a good way to think about this project. We'd really like to be able to show this application working. Well, go and download this application, see what it requires, see what we support, what we don't support in that application, and work backwards from there. To get this to work, here are three major features we would need to implement. And that builds up your entire rubric right there. And that would be a pretty cool way to do it. There is not a first come, first served aspect of this. I see it very unlikely that teams will be proposing the same exact thing. Maybe you'll be attacking the same problem, but I would expect it to be coming from different angles, just based on your personalities, your interest areas, and what you've been focusing so far this semester. So I wouldn't worry about that. If two teams wind up proposing the same exact thing, I would imagine the rubrics themselves would look different. So it'll wind up being a different project for that reason. Okay, well, I'm glad we had that discussion. We can continue to have this discussion, but the time to start thinking about that is now, while you are working on your MP3 assignment. And another reason I think it's good that we have a little bit more time to work on MP3 is we haven't really even synced up properly with lecture yet. So this is my attempt to kind of sync up. I think after today and certainly after Thursday's lecture, parts of MP3 that may make a little bit less sense than they should will hopefully make a bit more sense. And then I think we're pretty good in terms of syncing up for the rest of the semester. But this is the topic, talking about programmable shaders. What does that mean from an architectural perspective? And then what does that mean from the programming perspective? And we'll probably do more of the programming perspective because you are getting this hands-on experience of what it really means from the architectural perspective, this week. So to start with, I think we know why we care about having programmable shaders because we talked about this on the very first day of the semester. Before we had this idea of having runtime programmable shaders, we had this so-called fixed function pipeline. That's something I've brought up a couple of times, and we've seen some examples of that. By fixed function, it was a configurable state machine, this pipeline. It was a set of state variables and otherwise just dedicated, you can think of as data flow hardware that would do the same exact math no matter what. And things like doing our vertex transformations were possible in there because there'd be dedicated hardware who was only there, like in our MP0, to do matrix vector multiplication. What you as the programmer would then do would be to specify, here's what I want the matrix to be. That's what we refer to as fixed function. It's always doing the same math. If instead I wanted to divide a value by 7 before I did matrix vector multiplication, I would have to do that entirely in software. The hardware had no hooks in there to support that for me. There was all sorts of workarounds to get relatively realistic looking effects. It turns out that by doing enough passes of a fixed function hardware and using textures in somewhat unintended ways or clever ways, you can fool it into basically doing something that looks somewhat more programmable. Your textures were treated as intermediate results of the render, and just by doing rendering over and over and over again for a single particular frame you're interested in, you can alleviate some of those problems. But from a programmer perspective, all of those could be thought of as sort of functionality hacks. And so the relatively recent major advances is that having this real time programmable graphics that have these programmable shader processors. And this term shader is used in several different contexts here, but it refers to both things. It refers to both the hardware core itself. We have a GPU that has shaders on it. So that is the actual hardware for us. And it also refers to the programs that we are running on them. So maybe we can be a little bit more careful in our language and refer to them as shader cores or shader processors. And then the shader is being the code that's running. But you will see as you read documentation regarding this, the terms being used fairly interchangeably. So, Matt, that's a good question. It's something we've actually brought up briefly in the past, and Matt's question is about. It's not necessarily even more powerful. The cores themselves are extremely similar to what of the type we're talking about today. The micro architectural improvements from 2004 today for the individual cores are very incremental. What has changed is how many of them we can fit on chip, and the total number of them. To some extent, the clock frequency they can be clocked at, and some of the surrounding hardware has seen some innovation. So the question Matt is bringing up here is, to what extent do we need anything fixed function anymore? And the answer is it's not well documented. We had talked about this previously, that if you buy 2021 graphics hardware, you buy an NVIDIA GPU, an RTX 3070, I don't know, whatever the latest and greatest and most expensive thing is. Don't laugh. Um, do you get any fixed function hardware in there anymore? I believe the answer is yes, but to what extent I no longer know, and it's not well documented. So they would hide that in terms of triangle setup. You would still potentially see in documentation. NVIDIA also separately provides diagrams, when they provide any diagrams at all, for their compute view of the GPU versus their graphics view of the GPU. On the compute view, you see nothing that relates to graphics. And on the graphics view of it, it's the same exact hardware. The hardware itself physically isn't any different, but you'll see things like texture fetch units. So those are still there. There's still some hardware to dedicate to that. Is there a hardware rasterizer, or is it entirely running in software? Is not something that I know the answer to. If someone can find a definitive answer for that, um, I'd like to find out more, because it's not that obvious that yeah, well, we know quite a few people on the inside, but um, they also don't share that information with us. Um, but so that's a valid question. So we can still learn about this, and then the question of, we implement something that is a version of this combination of programmable and fixed function hardware. What 2021 looks like in terms of how much is still fixed function is not clear to me, and I'm happy just to tell you that there's no clear document that I've forgotten to read, that I just missed or something like that. How much is actually still fixed function? Is there still rasterization hardware? It may now depend on what the vendor is and what design trade-offs that they have made along the way. So when we talk about programmable shading, there's a lot of different flavors now of shader uh, language or shader task we are interested in, and we talk about how OpenGL has several different shaders available to you as the programmer. So much of the default examples you will read, and even many of the advanced ones, will still be focused on having vertex shading and fragment shaders. So architecturally, while we look at how the cores to do both are now effectively equivalent to each other, the goal of the programs, the shaders themselves, are still separate and different in our modern graphics libraries and languages. So the vertex shader as the program, its job is to do the computations we were talking about last week and before, to do the transformation from object coordinates to world coordinates to clip coordinates, maybe also to do the rasterization and viewport transformation as well. That part's not clear. And then the fragment shader, that program is to determine what the attributes of an output fragment is supposed to be. What should our final color be um, for that particular location that's going to be stored in our frame buffer. So initially it was done via some assembly-like language. Now there's lots of different language support for it. Um, in my analysis of the various languages that are available there to do this, um, they're extremely similar. And if you understand one, it does appear that transpiling between one and another is a relatively straightforward thing. Whether a tool already exists or not to do it, all the languages are supporting the same class of hardware, and we have talked about how the languages and the hardware kind of co-evolve. So hardware has capability and the language has to evolve to support that capability. Likewise, the needs of graphics programmer evolves with the language, and the hardware has to catch up to what we would like to do effectively in our software. Um, so I won't provide any examples this semester of what RenderMan, that shading language, can look like. It's still in use today. It's got some slightly different flavor to it because it's meant for non-interactive rendering. The first rule is sort of real-time programming, high-level language for programming shaders with CG. It's deprecated now by NVIDIA, but if you look at the CG examples and look at the language spec, basically the same thing. The changes have been very modest, even over the past 2 decades since the release of CG and some of the competing kind of academic focused languages there. There's the DirectX specific alternative, HLSL, which is still commonly used, and then there's what we're using this semester, GLSL. There's also a number of other really platform specific languages. So there's some embedded GPU vendors. They would have their own shading languages because they have other specific restrictions. And just like we're making the decision not to be fully compliant, they also don't necessarily or can support full compliance there. They're all extremely similar for whatever that's worth. Um, and there's no need to ever really fight over HLSL versus GLSL. They're extremely similar. So we learned GLSL to some extent this semester. It seems like the future is not really worrying about the source language, but having some well-defined intermediate representation instead. So that appears to be coming at least in the more open side of the graphics community with this SPRV, this SPIR-V intermediate representation. And then I think as long as your compiler can target that, you could call what you have a shading language. GLSL would be guaranteed to work, but as long as the things that you are using and you have a compiler that can target that intermediate representation, that then becomes your shading language. Um, and as we see here, when we'll look at these examples here, it is a C++-ish kind of syntax without any of the really truly sort of modern features of C++. But for the actual compute side of things, doing exactly what you would hope to be able to do in an object-oriented language targeted to computer graphics. So there is a GLIR. It's not called that. Uh, well, first off, historically, the compiler, and we will talk about that, was a vendor provided thing. So in your driver support for your graphics hardware that you were using, as part of that driver support would be an implementation of the compiling and linking and using of shader languages. And so whatever intermediate representation was there was whatever your vendor was using for their own implementation. It has somewhat standardized to an IR that's this binary format, this SPIRV. But that's a relatively recent phenomenon, um, and because provided as sort of the default implementation, I think that's a valid target to assume for your intermediate representation. So it's an LLVM style um, intermediate representation here. Another question here. Um, and going back to your second point, Matt, and that's a CPRE 482 question, but that's still very much a wild west with regards to intermediate representation from ML. There are many such competing approaches. Maybe you learned one in that class, and that would be a good thing to learn an example. But the graphics community is much more standardized than the ML community currently today. Certainly for intermediate representation. Um, well, the shader doesn't necessarily get compiled down to PTX. NVIDIA has their other SAS, I forget what it's called, their intermediate representation. But we will talk about what actually gets emitted from once we're using our NVIDIA compilers. It's a little bit buried underneath the scenes, but you can assume that there's several stages. But this intermediate representation then, in the case of NVIDIA, gets something of a just-in-time compilation to the actual assembly that's being loaded on the particular device. So backing up to Brian's question here, so would it be up to the compiler to make the program on a variety of GPU hardware? Um, we'll talk about the architecture of that. So that's a good question. So the individual shader, I think this is an important point. We'll go back to demos for a second here. The individual shader is intentionally written to operate in isolation from all the other shaders. So there's this concept of stream model of computation, but all the languages that one would use for this operate on that principle, where it's an individual thread of computation operating in isolation from the remainder of them. And then the rest of either the driver infrastructure or the actual hardware would together operate some sort of scheduling mechanism for these individual threads of computation here. And the reason I hedge a little bit about that is that it is a combination of both, right? Our driver infrastructure right now doesn't have to do that because we just have the one shader core. But at some point, the driver would have some knowledge about what is a reasonable upper limit of streams that are possible to have executed at any one given point in time. And then separately, and we will definitely talk about this, there's hardware mechanisms to also do that kind of runtime scheduling of these streams of computation on the individual cores. But that's why it's actually a solvable problem versus trying to approach more general purpose parallel computing. The shader languages and the execution model for these are such that they're, for the most part, entirely independent of each other. So when I talk about this, and this analogy that this is talking about fragment streams here, the same analogy holds for looking at vertex streams as well. Uh, is that you have an array of computers or array of shaders, and they're all running the same program. So that first off, that helps simplify the parallel programming model that's required here. They're all running the same program, and for the most part, they have very limited state and they're operating independently of each other. So when we write our shader code, when we rewrite our GLSL, that shader is written with effectively zero knowledge of how it's going to get executed. It gets an input, it calculates an output. It doesn't know, for the most part, anything about the ordering of which vertex will get processed when, which fragment will get processed when. And then that's the general mode of computation that GPUs have evolved to support. There's a little bit of a chicken and an egg here. I think that for computer graphics, that's a very natural match. I have a whole bunch of vertices I need to process. And for the most part, the algorithms that have been developed over time allow those vertices to be processed in a somewhat arbitrary order. And the same for output fragments as well. So as the hardware has evolved to support that, and we've effectively built these stream processors that run relatively very short programs and store little to nothing about what the execution state was of those individual inputs and output relationships, we've also then supported general purpose computation using that same type of architecture. So when I say chicken and egg, and we will talk about CUDA, we have a couple weeks to get to there. But when we get to CUDA and talk about unified compute architectures and doing general purpose compute on them, it didn't evolve accidentally. It was to reflect what hardware was already being built to support, which is this model of computation specifically for vertex and fragment shading, recognizing that first off, while maybe originally vertex and fragments were significantly different in terms of the type of programs we would like to run on them, that's no longer necessarily the case. And so consequently, the hardware can look the same. And secondly, our hardware was evolving to support as many of these being run in parallel as possible as we could support on a given chip at a time. That leads to a model of computation for general purpose computing that can map very well to that architecture. So, NVIDIA will pitch it as being two separate views of the same architecture. And there is some custom support for certain things that don't make sense from a graphics applications perspective. But beyond those kind of really just sort of side issues there, the architecture is still the same as what we were talking about today, which is these cores that support computing streams with an array that allows us to just take data in and pass data out. So this term kernel well predates the use of it in the CUDA context for NVIDIA's compute. And it just has to do with an individual program, be it a vertex or a fragment program, that operates on every element of an input stream and generates an output stream. Where ultimately, from the graphics perspective, that output stream is either transform vertices and then ultimately locations in a frame buffer. So this is a very general model of computation, right? All it's saying is this kernel is a small program that transforms input data into output data. And we can compose these kernels together to do some general task. But the kernels themselves, outside of the input-output relationship, have really no knowledge of what the others are doing. And they're not storing state from one execution to the next. So we'll talk about this in the context of graphics, but it's the same when we're going to start looking at general purpose compute. So I'm glad there's lots of good questions there, but we're a little slow. We're not quite there yet. But it's not a coincidence. That's what I was trying to get at there. That what we talk about here uses the same exact terminology we'll be using when we're talking about CUDA and general purpose compute. And so some of the questions about what is the intermediate assembly format and others are related questions, but it was a natural evolution of what was already happening for graphics. It wasn't necessarily some tremendous stroke of genius, but by some very smart people, working at NVIDIA, realizing that they can use this for compute. The hardware was already being used for compute, using languages like GLSL and HLSL and CG, and the recognition that we can provide better language and runtime support for doing general purpose compute using effectively the same exact hardware that we already are going to be talking about today, which was designed to do vertex and fragment shading relatively efficiently. I wanted to start us off with a quick demo, though. We had previously opened up that Shader Toy website. That was early in the semester, and it blew up my Google Chrome, and I couldn't actually show it in the stream, and it started to block and slow down Zoom here as well. This shader editor, and you can go to that website, is a little bit better for playing around with shaders. I mean, to be frank, the code that's provided for MP3 is also sufficient for playing around with shaders. This one's a little bit more user friendly. I can briefly open it up here so you can see what I am talking about. Let's refresh it here to make sure it's okay. So what it provides is similar to Shader Toy, but let's see if I can make it a little bit larger there. But targeting much closer to the vertex and fragment shading and the type of shaders we can run with examples in source here. Bit of a caveat that I mentioned that the type of things we do with shader languages has not really changed since 2003. The syntax has changed. So I don't think we'll run into that too much this semester where you'll struggle with that because I'm giving you examples and you're modifying those examples versus starting from scratch. But for example, even though I really like this website and its use of a version of basically WebGL, this is using a syntax that's currently deprecated. So it's fine. We have a replacement for um, all of these exact syntactical fun things here. We don't use the keyword attribute anymore, but you should be able to figure out what that means, right? We've been talking about attributes all semester. We just call them inputs to a shader now. Likewise, uniforms we still use, but varying, you may be able to determine what varying means. It means something that varies across our triangle. Those are just outputs of our vertex shader now. So syntactically, some things have changed, other things haven't. So that is always a problem when working with OpenGL. And I mentioned that on day one of the semester that you can Google for how to do something in OpenGL, and you have to look very carefully at what version you're reading from, what the exact syntax is. Is it the version that we are wanting to support? Is it too new? Is it too old? Is it just right? That's what makes this not terribly fun, but conceptually, it's all basically the same thing that's happening here. So I kind of like this website because it lets you very easily decide. It doesn't actually show you any of the OpenGL code, for better or for worse, right? But it does let you specify your vertex shader and your fragment shader here, and this is doing per fragment lighting of a very basic type, um, which we'll get a chance to talk about, excuse me. And then it's specifying our uniforms. And you can also say, without having to change any OpenGL code itself, that I would like to actually change the mesh that I'm rendering here. So that now we're back to our teapot with the texture map to it, and that's just a one-line change here. Um, we can make it a person's head instead here. Well, you know what? That gives me an idea. One second. I have an idea. That's good. That wasn't the idea I had. Okay. Um, we'll get to that in a second. Not of my face. That would be nice. But what is a texture map, right? Texture map is usually just a 2D image of someone or something. There we go. So it seems to be working as expected. But now if we make it his head, well, that looks about right. So that anyway, this is why this is a good thing. Okay, yeah. That looks about right to me. That's why I think this is a pretty fun little website for playing around with shaders. That Shader Toy is also extremely fun, but it's a fundamentally different rendering algorithm that they're doing here. This is our traditional OpenGL rendering algorithm, and you can very quickly without having to change a single line of OpenGL code. Change things like, what is the shape that I'm rendering? That looks about right. What is the shape that I'm rendering? Um, you can change the uniforms associated with it, and we can start to play with the vertex shader as well. Now, by default, this is doing our forward transform, right? This is doing, there's a single matrix specified, which is our model view projection matrix. So that should sound kind of familiar from last week, but we can review and talk about that if need be. And it's doing that matrix vector multiplication, right? Input vertices are coming in. They're specified as a vec3, and we will talk about that. We just add the 1.0 to it so we don't have to basically waste the bandwidth and specify that W component there. And we're doing that matrix vector multiplication, and separately we're calculating the surface normals given the position vectors we have there as an input. We can mess around with that as well. So we also have other normals that we're not using here. So time in seconds. Um, what can we do with time in seconds? Is that it's not a uniform provided here. So we can mess around with it. So instead of just all of vertex, we can just specify, I don't know what that did. Um, there we go. That should be equivalent there, where we are specifying just the X, Y, Z perspective. Let's change the X over time. Well, so that didn't look terribly good. As time is increasing, X parameter is going into outer space. Um, Well, but it's time in seconds is the problem, though, right? Because so given time in seconds, that number is just going to keep going up. If I make it small enough, what happens here? Okay, so now we have, if you remember Superman, the original movie back in the day, kind of trapped in the time cube there. So anyway, it's kind of fun to play with. You got to kind of think of an idea first, and then look at the syntax for how to do it. Um, but each of these programs are then being executed on the individual vertices as they come in, and whatever other attributes are associated with those vertices are something that you both specify in your OpenGL code. There's a vertex fetch unit whose job is to grab those, and they get copied into your processing pipeline here, and then those get associated with variables of a certain type in your shader code here. It's possible that this is a little distracting. At the very least, we could stop moving them around. That's better. Um, and each of these are individual programs that are running on a point by point basis or a vertex by vertex basis. Takes an input, not that obvious given how we are doing this here, to be frank, but it's providing three outputs here, given this syntax. One is, and it's something of a required output of our vertex shader, an output position. What is my location in XYZ space after doing whatever math I'd like to do on that input vertex? This shader itself then specifies two other outputs as well. One is the texture coordinate, which we haven't talked about at all, and the other is the, it's not exactly light information, but the normal to the individual vertices that we have there. So to help us do light calculations, that is the output of this vertex shader. When we then now have a corresponding fragment shader, I like the way you're thinking here, though. Thank you. Now we should have the corresponding fragment shader time. It's underscore time. That looks wonderful. So that was a wonderful idea. Thank you. Uh, um, don't let me play around with this stuff all day. It's not good for me. Um, what could we do with that? Anyway, fine. The corresponding fragment shader would then have as inputs the output of our rasterizer, whether that's fixed function or not. But from a language perspective, those inputs to the fragment shader have to correspond to our outputs of the vertex shader. So as we will walk through all the steps we have to do to actually do our compiling of the actual shader code, and that syntax is pretty annoying. And we played around with a little bit of it. It's probably the reason if you're Um, well, we'll get to that in a second, but it's probably the reason your MP3 code is not working for the older applications. We have to go through all those steps of compiling and linking the shader and loading the shader for that Vertex shader module to actually do any processing of inputs to outputs. That's the step where it's actually checking those things. So compiling the shader is just a syntactical thing, right? We had a syntax error just now where I had the name of the uniform variable wrong. Um, okay, there we go. Um, maybe we can slow that down a little bit. Anyway, we need to move away from that. We'll just play around with Jones's head all day, and that will be not a good use of our class time. But so there's the compile. That's the syntax compilation. But then there's a separate step of sort of linking the shaders together into a single program, and that's where you're going to find some errors that may be a little bit harder to debug. But what that is effectively doing is checking: does the output of my vertex shader map to what my inputs are of my fragment shader by name, by variable names here? And the kind of errors you get will be a little bit opaque. Sometimes the compiler will apply some optimizations that will cause things to fail, but in general, that has to be the map to each other. And that is something of an artifact of the genesis of this idea of having physical vertex and physical fragment shaders in our hardware. So this is an example of a very early, not the first, but a very early programmable GPU hardware where you would have physical vertex shaders and physical fragment shaders, and they would be physically resident at different places in your architecture here. So from you can look at this as from top down, and it's not so different from what we have already been talking about all semester as our graphics processing pipeline. This is still a pipeline here. We can see a lot of MP3 going into MP4 in this diagram here, except that just ours is a much more narrow version of this here, right? Where you would physically have this connection between the two. We'd have our stream course here. We'd be processing our input vertices. We would then have, doesn't exactly show it as the rasterizer, but that's effectively what this would be here. Taking our triangle setup, that should sound familiar, generating our fragments based on the output of our vertex shaders that have all the attributes defined in our vertex shading program itself, and then kick off our execution of our fragment shaders that we would have here until we go to the next part here. This would be, we're doing texture, we're doing our render output, we're doing some more fixed function stuff in this lower part of the architecture that we would have here. So certainly in the early days, we did think of these things as being completely separate from each other. You would buy a GPU that would have a certain number of vertex shaders, the physical hardware, and a certain number of fragment shaders. Generally, the number of fragment shaders would be larger than the number of vertex shaders. We've probably already seen why that's the case, right? We specify 3 vertices, and maybe that's 20 fragments, but maybe that's 2,000 fragments, maybe it's 2 million fragments, right? There's an imbalance relationship between the two. 3 vertices is always one triangle, but one triangle can be a somewhat arbitrary number of fragments. So the exact ratio of fragment shaders to vertex shaders is something that different architects kind of toyed with over time, but generally always the fragment shader was larger than the vertex shader. But otherwise, given this fixed function hardware in place, otherwise what was actually happening uh, from the ISA definition here, from the microarchitectural implementation here versus here, from the very early days was extremely similar. Depending on the architecture, what generation we are talking about, vertex shaders couldn't originally access textures, and now they can. Vertex shaders couldn't originally have much in the way of control flow, but fragment shaders could. There were very small differences given the needs of graphics programmers of that era, of that time, but the differences were extremely small in nature in terms of the functional units that were implemented, in terms of the fetch, decode, execute implementation of these individual pipelines. You're looking at very similar looking things here from the early days. And so as we have evolved over time, for which we would go from a device that would have perhaps 6 vertex and 16 fragment shaders to one that would still instead just have 22 shaders of either type, of an arbitrary type or of a uniform type, the actual changes of what's happening inside here is relatively small. Um, couple more questions in the chat. I never want to ignore you guys when you're asking questions. Yeah, okay, so that was your question. Yeah, extremely similar. Less similar at first, maybe almost with sort of intentional differentiation between the two. You can kind of see it architecturally here, but over time becoming exactly the same of what you can do. Syntactically in GLSL, there are some rules, I would describe it, for what can be done in a vertex shader syntactically versus in a fragment shader. In terms of the vertex shader always has to output a position, and the fragment shader should always be outputting a color. So there's some rules assigned to it. But in terms of the math that they're capable of doing, in terms of what the underlying ISA is, it is identical. They are exactly the same, not just very similar. Um, for us, in our implementation, we still, I think, see some value in implementing this pipeline from top to bottom. Again, I mentioned a very narrow version of that pipeline because we're going to implement one of these and one of these. So it's the same, but it's a very narrow version of that. I think for our purposes, the ISA is going to be identical. If you look at the MP4 documentation, which again just tells you to get started and go do it, um, I tell you to actually literally copy your vertex shader core and rename it to fragment shader because they should be identical. So we are, for better or for worse, doing a unified shader architecture, even though we're physically still placing them at different points in the pipeline. That's a debatable design decision. One of our design criteria was simplifying this vertex fetch side of things, which can get incredibly complicated to have a much more static and structured DMA style of vertex fetch here. Feel like we've lost the plot a little bit with the sinusoidal Jones's head. Talk a little bit about the plumbing of shaders, the different data types. Um, to be frank, though, I do feel like you can sort this out. Given some examples. Um, Thanks, Ryan. I'll try that once class is over. Given some examples of shader, I kind of trust, given what you've experienced in your curriculum and other activities so far, you should be able to figure it out. There are some restrictions, though. So, given this stream model, and given certainly from the early days the understanding that in a streaming model, we'd like to have these cores execute in as much lockstep nature as possible. That has some implications for how we do control flow. But in terms of syntactically what the shader allows for, it looks very C like. Actually, the best thing I could compare it to is that if you've been playing around with that GLM library for MP3, some of you looked at it for MP2. Um, it's doing the same exact thing. That GLM was invented to give this OpenGL interface to doing the same exact kind of interfacing and processing of inputs to outputs as what GLSL provides. So typically your data types are floats, although you can have other data types as well. Then you have vectors and matrices as first class objects in the language with arrays as well. And then we do specify 3 different types of data. The keywords we use for that have changed over time, but the concepts are still the same. Um, you would have your per instance data. That's what we've been calling our attributes. Per vertex data. That was called attribute. We just call it in our vertex shader. Then we have our per pixel interpolated data. That was the keyword varying we just saw. From the vertex shader's perspective, that is an out. From the fragment shader's perspective, that is an in. That is the output of your rasterizer, all the interpolated data. And then there's our per draw call or per batch constants. That's our uniforms. Those are constants in the sense as you can assume they are the same for the entirety of an individual GL draw call, GL draw arrays, or whatever subset we use. Teams haven't gotten to this point yet. That's actually a tricky thing to do properly in your hardware. So you do have to be uh, more aware now than what maybe most of you had to think about for what happens at the end of a draw call. I know we've put some effort into how we synchronize the end of the draw call. How do we make sure we don't swap the frame buffer until it seems like the previous draw call is complete? But now from the shader's perspective, some things are per draw call. When I'm referring to this per batch data, those are the uniform types in our OpenGL. Those can be they're not required to change, but they can be expected to have changed from one draw call to the next. So you have to be aware of that. But the rest we can kind of treat as just in our implementation as input FIFO, output FIFO is from the vertex and fragment shaders perspective here. Very simple flow control. This has changed over time. In the very early programmable shaders, there was essentially no flow control allowed. You could have if statements, but they would be constant ifs, basically pound define ifs. Still today, for many variants of the shader model that you'd be supporting, they still don't support recursion in the flow control. Um, we'll talk about architecturally why that's the case when we get to our unified shaders and our compute models. Again, the idea of the parallelism that's available in this stream processing is that we have shaders that are effectively operating in lockstep with each other with very little state associated with the execution. That is not impossible, but hard to kind of marry with the idea of having complex control flow in the shader code itself. If I have a series of very complicated if statements in my shader, then what will happen is, while we like to think of these streams as being completely independent, we'll have some streams that are on a certain point in place in the shader core in the code, other streams that are in a completely other different place. They don't have to necessarily be synchronized with each other, but architecturally it makes sense to have some shared resources there, and we have to be careful for that if we want to support more complex control flow. At the very least, though, there has always been support for doing things like discarding fragments. Um, that's a type of control flow. That's basically telling your fragment shader, uh, don't continue for whatever reason. We want to add some random noise into it. We don't want something that's outside a certain range. We're doing some sort of clipping in shader software versus some state machine based clipping happening here, and that's that keyword discard in GLSL saying we want to get rid of that particular pixel. So what our vertex shader is generally doing is that transformations we were talking about last week. So given X, Y, Z, and what other attributes we have, get our objects into a shared common coordinate system that allows for easy fixed function process to happen afterwards. So could be at the very least, you have some sort of input vertex positions and whatever other attributes we want to specify. Our implementation um, is limited by the fixed number of attributes we have. There is an upper limit even in your OpenGL, but it's larger than our 16 total floating point attributes that we provide with the outputs to the rasterizer. So um, we kind of see that we've kind of already been assuming that vertex processing is happening, but that's the whole point of your MP3 hardware. So at the very least, it's doing some sort of transformation, even if that transformation is via an identity matrix. So at the very least, what you tend to see in your vertex shaders, as was the example that we had in our uh, Creepy Jones face, is that matrix vector multiplication here. That's the transformation that's happening in that example here. Architecturally, though, what we have is going to wind up being extremely simple. This is maybe a slightly overly simplified version of it. But there's a question in chat about Tomasulo's algorithm, and that's something that you learn in 581. If you haven't taken 581, you don't have to worry about that. It's an approach to allow for many different potential types of instructions to be executed concurrently with something of a scoreboarding algorithm implemented to allow us to make sure that we get the results back in the register file or in memory the way we want them to. Um, that is a particular type of parallelism. These streaming cores use a much more simplified version of parallelism. And there is a reason why you can have, without too much effort, 32,000 threads running on your GPU without really even thinking about it, whereas such a thing is fairly unfeasible on your traditional CPU. From the GPU's perspective, from this shader core's perspective, as I mentioned, there's very little state. We take an input, we run our program on it, we let the program finish. There is some scheduling and hardware that has to happen here, but it's a much more simplified version of it. We have instruction fetch, instruction decode, and instruction execute here. And then we're done, generally. There's a feedback loop being shown here because in theory there is some sort of branching and supporting that is possible there. But in general, It's much closer to that kind of data flow hardware we built for MP0 than it is to anything else. Because the actual code that we're limiting ourselves to, the programs we're limiting ourselves to, aren't going to require us to do things like overlap execution from four different threads and trying to take some assembly instructions from this thread and some from this thread and kind of merge them together and get the results back out in a way that's still correct. Each of these shader cores is looking at a single task at a given time, executing a single kernel at an individual time, in which the output results of the first input's execution is completely independent of the output results of the next input's execution. So while there's still data dependencies and the like, I mean, that doesn't go away. You still have registers. You're still writing the result to registers and then reading the results from registers. So there is still a physical pipeline. We don't have to worry about a very large number of the issues that come up when we try to take our traditional deep pipelines and get thread level parallelism into it, or even just more instruction level parallelism. There's still some scheduling going on here. This doesn't show it, but one thing that you've probably already seen is if you want to get square root working in MP3, give it a try, but after you've gotten other things working, um, that is going to require some custom hardware that's not going to interface very cleanly with the rest of the pipeline that you may already be building. And that's the case today in modern GPUs as well. That we have these special function units. That's what NVIDIA refers to them as, for things like exponent and inverse square root and the like. Stuff that gets used, stuff that is necessary, but cores or ALU functionality that's not used nearly as frequently as things like addition and multiplication, load and store. So first off, there tends to be fewer of them, and they tend to be shared amongst multiple shader cores. But secondly, we tend to just have a larger performance hit associated with that. So as you implement that, you may find that's the case. That's still very much the case. It's not as tightly integrated. It's not being shown in this picture here, but it would be part of your modern shader core implementation that you would have not just vectorized multiplication and addition and very basic stuff, also somewhere to the side here and potentially shared amongst multiple vertex processors, a piece of hardware that can do sine of x very effectively for you. Let's leave things here for today. We kind of lost the plot briefly along the way, but we had to cover the project too, so that was important. On Thursday, we will continue with this. I don't think we'll finish it at the rate we're going, but we will continue with this on Thursday. Tomorrow's lab. I still like you to push very hard on making progress on MP3. I don't see any teams who've made any real progress yet. Maybe you've been very quietly making real progress, and that's you don't have to showcase. You don't have to show me your progress. I understand that, but I don't think we're ready for a Thursday demo day. So we'll do our MP3 demo day a week from today. Hopefully, giving you enough time and kind of balance out with other classes that you have. And then on Thursday in class, we'll just continue with this topic. Let's leave it here for today. Come stop by office hours if you have any questions, but certainly if you have project related questions, maybe meet as your team briefly first. But I'm really happy to chat about project ideas, give you my take on what I think is feasible, what I think may be too much of a reach. It's very unlikely I'll tell you that any project idea is too easy. That tends to be not the kind of project ideas students in this class come up with. So let's leave it here for today. I'll see everyone tomorrow in lab.